Hi, in this video what I want to do is just have a bit of an overview of the reactions that we cover in first year on the functional groups of both ketones and aldehydes, and we can treat them both the same. As a general sense, if I just draw up this ketone, this is butanone, and we can see here is the carbonyl group, a C double bond O, and this is a ketone. But everything we're going to be working with, and I'm going to show you now, is applicable to both aldehydes and ketones. And very simply, as a generic kind of example of the reactions that we are doing with this, is we can take a nucleophile, and as you study organic chemistry, you'll find that there are actually a whole host of different nucleophiles, but this is just an archetype of one. We're showing just NU to stand for nucleophile. We could have a lone pair of electrons. It might have a negative charge, it might not have a negative charge, but there is a lone pair of electrons, something that can add to the carbon. And this is the key here, is that the carbon of a carbonyl functional group, or in this case a ketone, this carbon over here is electrophilic because the oxygen is more electronegative, so it's delta minus, and this carbon is delta plus. And so because of that, nucleophiles, which have electrons to donate, are able to donate to this carbon because not only is it slightly positive, but this pi bond that is associated with this carbon oxygen double bond, the pi bond is actually really weak. And so it is easily displaced. It's almost like a placeholder on this carbon. So we can add those electrons to that carbon and this pi bond can break. And in a very simplistic sense, this is the type of reaction that occurs, and we'll get a nucleophile and an O minus because those electrons have now ended up onto the oxygen over there. So I'll just color this in. There's the nucleophile, and now we form this new bond over there, which is came from those electrons of the lone pair. And then typically at the end of this sort of reaction, we've got an O minus, is that the oxygen will be protonated with some acid. So there'll be maybe some acid present. It might be a second step. It might be part of the first step. And we would get a final product that would look something like this. All right, now it's all very well that this is the archetype. All right, this is not a true example of a particular reaction. We have to actually look at the different types of nucleophiles that we can react, because each one has a little bit of a trick in terms of what the final product is. So we're going to look at that carefully. In our first year course, we're only looking at 3, so that actually makes it quite easy. The first one that we're looking at is Grignard reactions. So that's some sort of carbon group with a magnesium bromide on it. And the sneaky thing with Grignard reagents is actually the nucleophile, and this is a bit weird, and we'll discuss it more in second year, but the nucleophilic part is the 2 electrons that are part of that sigma bond between the R group and the magnesium bromide. Okay, so it is a little bit weird. The second one that we look at is, again, some sort of R group. It could be any alkyl or aromatic group, is one which has an OH on it. So we're looking at the alcohols. And the alcohols, of course, have lone pairs of electrons. And that's the nucleophilic part of that. So the alcohol part, the O, is the nucleophilic part of that nucleophile, which we're going to add. And the third one that we look at is amines. We're just going to look at a primary amine. We're not going to look at secondary amines in this course. So it's fairly simple. And there we go. There's that lone pair of electrons on the nitrogen, making that the nucleophile. So let's just look at all of those 3. Again, we're looking at this very briefly. We can actually go into much more detail for each one. I just want to see the pattern that is emerging over here. And that is when we add a Grignard reagent, what happens here, it's very much like this archetypal picture that I've drawn up over there. So I can take, let's take a simple, in this case, I'm going to take an aldehyde and I'm going to react it with a Grignard reagent, and I'm going to choose to use the benzene magnesium bromide. And the key here again is that the thing that's going to be the nucleophile is this little bond here. And what's going to happen is that's where the lone pair of electrons are going to add to this carbon and we break that over there. So this is going to become the bond to the benzene, and the magnesium is going to move away. And so our product looks like O minus, and we've added this benzene ring to it like that over there. The H, we don't have to draw in. It doesn't matter because it actually it's always hidden on our skeletal structures. Here's the benzene ring over there. There's the benzene ring over there. And this bond over here is the bond that had the electrons in it in the first place. Right. And then what happens in Grignard reactions is that actually one of the tricks with the Grignard reaction is the fact that Grignard reagents themselves are incredibly strong bases. They react so quickly with acids that this archetypal reaction that we're showing over here, we have to add acid second. It has to be a part 2 to the reaction. We can't mix this with acid. It will kill it. It will die. It will go back to just benzene and give us hydroxide from the water or whatever might have been present. So we can't use water in this reaction. We have to only add it as a second step, which is adding H3O plus mild acid just to give the final product, which will be the OH over there. All right, you do it to this side over here. So we would get, I'm changing it to pH now, and we end up with OH over there. So here's the phenyl, pH stands for phenyl, which is the benzene ring, and there's our bond over there. All right, so that's just an example of that. So the trick with Grignard reagents is that when we do the addition, it's actually the sigma bond that is adding, and then this is the substituent that's adding on. We add to it, and we end up with an alcohol, and we can only add the acid as a part 2, all right? It can only add afterwards. It mustn't be added during the reaction. It won't work. The reaction will die. With alcohols, it's actually, from a mechanistic point of view, is actually a lot more complicated. And for this, I'm going to take a cyclohexanone as an example, like this. So this is a ketone. And when we add an alcohol to it, and I'm going to choose to use, in this case, I'm going to use methanol, right? So this is the R part of it over there. Okay, that's the R part of that. Color that in. And the nucleophile is this oxygen over there. The product, we must always assume that when we add alcohols, we always assume that this is actually adding in excess. It's a 2-step process. You can go and look up the mechanism of this. It's quite an elaborate one, but when it adds on, it's a 2-step process, and what we get is this functional group called an acetal, O-M-E, O-M-E. The secret here is that the oxygens of the OME actually came up from the methanol itself when it was added. Now, another secret with this one over here is that actually this reaction is an equilibrium. 2, we have to have an acid catalyst. Now we're not doing this in 2 steps. It needs to be in 1 step together. Because it's an equilibrium, we can use Le Chatelier's principle to control these types of reactions, and they're very, very useful in organic chemistry. So please don't think that this is useless because it's an equilibrium. This is a very important reaction in organic chemistry to make an acetal. If we want to push the equilibrium to the right, what we need to do is add lots more alcohol. All right, so we add more of the one reagent, it pushes it to the right. If we want to go to the left, the clue is that the product of this reaction was water, all right, and this oxygen is actually this oxygen over there. And if we want to go all the way to the left, it means we need to add more water, and we can push it more in this direction over there. All right, so at the end of this video, I will do the mechanism of this one. And then the last one is the addition of an amine. Okay, we're only looking at a primary amine. Again, it's a nucleophile that's adding on. And the trick over here is that actually, whereas an alcohol adds twice, like this, over there, the Grignard reagent adds just once, only goes on like this. alcohol adds twice, and we get the acetal. The primary amine only adds once, but we get a double bond. And so what we get with this, so I will take a open chain ketone, it's still just butanone, that's up over there, and we're going to add isopropyl amine. Okay, so this part over here is our nucleophile, lone pairs of electrons on the nitrogen over there, and this part over here is our the rest of the molecule. Now the nitrogen is still connected to all these carbons, and in the product that we get, we're going to get it looking like this over here. And notice that this remains, all right? This whole part over here, which is part connected to the nitrogen, remains still part of this molecule. And what we've also done is we have given off some water. So this too is actually an equilibrium, and we also need to add acid to it as well. All right, we have to have acid added as well. And this forms the functional group called an amine. Okay, so this is the overview. This is the things that you need to know. What I want to do now is I'm just going to show you the mechanism, which might help you understand a bit more where these are coming from. All right, it might help you understand where they're coming from a bit more. So let's look at it. The mechanisms do take a bit of time, so that's why I'm just doing them last. So I'm going to start with the acetal mechanism. And what happens here is, remember that this over here is the electrophile. And we had methanol, which I'm going to draw out like this. There's CH3. We had methanol as the nucleophile. Now, it turns out that for this to add here is not actually that favored. And what we need to do first is we actually need to use our acid catalyst to protonate our ketone. When that happens, after protonation, we get this oxonium intermediate, which can now be attacked by our nucleophilic alcohol. All right, so the alcohol goes in like that, and we kick out, and we end up like that. Now, I'm already starting to do the mechanism by making a very small mistake, which is actually important, and that is that each of these steps is actually in equilibrium. Remember what I said to you, that this reaction I'm doing is fully in equilibrium. That means each step is actually reversible. So we can add this in, and it can also come out again as well in a reverse fashion. So what do we get after that? Well, that added there, so it made a new bond to the oxygen, and this is still connected to the CH3, and that oxygen had a hydrogen on it over there, so it's now positive. This sigma bond is going to our oxygen. We broke the pi bond, okay, so it's positively charged, went over there, so it neutralized, and we've got this H bonded to it over there as well. All right, so we've added the first bits over there. I'm just going to color code this now. This part over here is the methanol. There's our methanol over there, and there is our methanol part over there. All right. Okay, the next step is a proton transfer. What we need to do is we need to get this alcohol to leave as a good leaving group. And of course, it can't just leave as OH minus because we know that is a bad leaving group. So we need to get this proton to go onto that oxygen over there. And there's a number of ways we can do it. And it may not be 100% correct, but let's just say that this is okay to take that proton over there and for this proton, that sigma bond to break so that oxygen over there becomes neutral. And so again, this is a equilibrium. And what we often do in our mechanisms is we write there PT. It stands for proton transfer. They've just gone from one oxygen to the other one. And actually, I hope you can see that that's fine, that there really isn't any problem with regards to that actually happening, because in this case, oxygen is protonated. In this case, that oxygen is protonated. They've just swapped partners. So here's the part of the methanol that's remaining. All right. At this stage now, this has been turned into a good leaving group. And mechanistically, it may not be obvious why this happens, but people have worked this out and they know that this is the way that it occurs. So it is a bit of an odd one, but the lone pair of electrons of this oxygen kicks in and helps to kick out that leaving group. In other words, the leaving group doesn't just leave by itself, but it's assisted by these lone pairs of electrons kicking in. And so we get a double bond with a CH3, and of course the oxygen is now got 3 bonds to it, so it must be positively charged plus. Water was given off in this reaction, and so there again is the part of the methanol. What happens next is another molecule of methanol can now come in, and we actually repeat the whole process over again. So it's very close to the end now, but you see that this is basically the same sort of thing as an oxygen is positively charged with a double bond. It's exactly the same as this over here. There's an oxygen, positively charged, double bond. It's activated for nucleophilic attack by this oxygen. And so lone pair of electrons can add there, and that comes up. I should color this one in as well because the next molecule comes in. Again, remember, this is an equilibrium that's occurring, and the net result of that looks like this. CH3 and OCH3, and there's an H on there still as well. All right, we didn't break anything over there, so it's still got that one over there. And so this is the whole thing all together. And the last step that gets us to our product is we just need to get rid of that H. It needs to go off. And what can pick it up? Same thing as we did over here, all these different things is fine. We picked up an H in the beginning. It was probably came from H3O+. Now we're giving it back, so it's going to leave as H+ or onto water. It's actually acceptable just to show it leaving like that over there. But we should think about the fact that it is actually being picked up by something, almost certainly water. So OCH3, and we get our acetyl functional group over there, which is 2 oxygens singly bonded to a carbon center over there. All right, so that's how the 2 molecules of methanol. Now, this reaction over here can happen with any alcohol. All right, it doesn't have to be methanol. It could be any other longer chain. The only one which is actually more interesting for you to just watch out for, and I'm going to just put it up at the top over here, is just in case there's a molecule with 2 alcohols in it. And this is a typical one because it gets used a lot in organic chemistry. So let me just draw out acetone, and so it'll look something like this. All right, so here we've got 2 alcohols, 2 nucleophilic bits that can add to there. And what happens is we get a cyclic acetal now when we need to add some acid. And what happens is there's the 2 oxygens, which are connected by 2 carbons like that. All right, so they're the 2 oxygens, and they are all connected together like that. So this part has been replaced by that. So that's the only one you need to look out for. Just be careful. It does make these are more stable, and that's why it actually forms that. So hopefully this mechanism just gives you a bit of an insight into the steps that are occurring. And the last mechanism I want to do is just the mechanism of imine formation. And so let's take this one, and we're now going to react this with a primary amine, and I'm going to choose propylamine like this. All right, and so this is the nucleophilic part, the molecule, specifically the lone pairs of electrons, but that's the whole molecule. They're all connected to each other, and the amine can add to the carbonyl over there like that. Now, I'm going to draw this out, and I just want to say something about this. So look, there's 1, 2, 3 carbons, 1, 2, 3 carbons. 2 hydrogens are still connected, so let's draw both of them in over there. It means that the nitrogen is now positively charged and the oxygen is negatively charged. Okay, so in terms of this overall, here's the whole thing that's added to it. In terms of this mechanism, many mechanisms will look like that. And for the previous one, the acetyl one, which we know needs to be acid catalyzed, you would have remembered that I protonated the oxygen first. It's still good practice to do that in this mechanism, but often in textbooks you'll see it written this way where they haven't protonated first. The only reason this is okay is that nitrogen is actually a much better nucleophile than oxygen. You don't need to know this at a first year level, but I'm just telling you at this point here. So the second step, remember this is also an equilibrium. The second step is also, again, a proton transfer. So this O minus can pick up that proton over there. And so we end up with NOH and still got one H over there. And the next step now is the same as with acetal. We need to get rid of this OH over there. What's going to happen is, so this was a proton transfer, we can do another proton transfer to make this into water. It's going to pick up the proton from the acid. It can't pick up this one because it'll make an N minus, and N minus is very, very unstable. So it picks it up. So we write down proton transfer. It picks it up from the surrounding medium. This is the catalyst that was added. And now we've got a good leaving group, an OH2 plus, and we've got a nitrogen with the 3 carbons on it, and I'll put the hydrogen over there. And now what happens, how does this leave? Well, the same as with acetal formation. You have this lone pair of electrons kicking in, and there was the whole thing over there. And the only difference is that this functional group is now basically stable, except for this H that's on there, which just needs to go away because this was acid catalyzed. If you count everything up, you'll see that the H's that went on also came off as well. Obviously, there was water over here that was given out. And we lose this, so the electrons go back onto the nitrogen, so it leaves us H+, and we end up with this functional group over here, which is an imine. Okay, so again, it's a long mechanism, all right? They're good mechanisms to practice in terms of learning how to push our arrows correctly and show mechanisms. From that point of view, it's very good. But it is a lengthy mechanism to do. The most important thing is to recognize the differences between the 3 different nucleophiles that we add. So going back to our original story over here, Grignards, when they add to ketones or aldehydes, they just add once, and we end up with the alcohol like that. Alcohols, when they add to ketones and aldehydes, they form acetals. They're normally in excess, all right? Normally in excess. The formation of, you will have learned as well, I'm not dealing with it in this thing, the hemiacetal is something that only happens really in sugars. It's a very specific example, which is like halfway of the mechanism of this case over there, and you should go and read up about that. And then primary amines, so just it needs to be an NH2. Primary amines, when they add to a ketone and aldehyde, they form an imine, which is a nitrogen with a double bond. But notice the part that was part of the primary amine, this part, whatever it might be, is still connected to the nitrogen. Same as in the acetal, but whatever is part of the alcohol is still connected to the acetal over there. All right, I know it was a long teaching, but hopefully it was helpful.